I'm Rufus Griscom.
And I'm Caleb Bissinger.
And this is The Next Big Idea. Today, is AI really that different from the human brain? Caleb, I thought it'd be fun to introduce this one together and share a little background on how we go about selecting the books and brilliant guests we have on the show.
Well, I mean, I hate to spoil the mystery for listeners, but I think the honest truth is that it's not a very scientific process. We just comb through dozens and dozens and dozens of books until we find one that just grabs our attention, that just makes us sit up in our chairs. And a couple of weeks ago, I saw this book called The Emergent Mind, How Intelligence Arises in People and Machines. It doesn't come out until October 21st, but I sent it to you right away, and I was like, how soon do you want to get these guys on the show?
Right. And clearly my answer was frickin' immediately because we recorded this almost 2 months before the book comes out. So this, I think, is a treat for folks. This is, I believe, the first interview that they've done. And I, of course, feel entirely transparent and predictable. As you know, I've been fascinated by this notion that our brains and the brains of every other animal, even insects, are shockingly similar in their components and structures, same neurons, ganglia, many of the same neurotransmitters as other animals. And though individual neurons can't think on their own really at all, something magical happens at scale. Intelligence emerges. And now we're building this AI and neural networks that are similar to our own. And it feels like an opportunity to better understand ourselves and study how that sophisticated thinking emerges out of relatively simple components in both silicon and carbon, our own biology.
I should pump the brakes on you a little bit because I think what's interesting about this episode is that it's partly about the ways that our brains and AI are similar, but it's also about the ways that they're different, right? And what makes our brains unique. Like, we're super multimodal. We're drawing inputs from what we smell and touch and hear and taste, and AI is not having sensory experiences like that yet, you know? And we also have long-term goals. We have emotions, right? Those are things that for now seem only to be possible for vulnerable biological organisms like us. So there are key differences.
Well, it's not the first time you pump the brakes on me, and for good reason. I need...
Producer is Latin for pump the brakes.
Well, this is... So sometimes I need some brakes on my enthusiasm. But what is so cool, actually, as you say, the human brain is different, and we're continuing to learn from the human brain about specialized approaches that we can build into the AI models to make them more capable to the extent that we think that's a good idea.
Yeah, it's this incredible symbiosis almost where like AI is sort of modeled on our brains, and that in turn is teaching us things about how our brains work. And we can now use AI to test theories about the inner workings of our own brains. It's kind of wild stuff.
It's extraordinary. And we have today the two perfect guests to talk about this fascinating dynamic.
We sure do. So one of them is Jay McClelland. He's a professor of psychology at Stanford, and he's really a pioneer in the field of AI. His work on neural networks has shaped how today's large language models are built, which probably explains why he's also a consulting research scientist at Google DeepMind. And Jay is joined on mic by Gaurav Suri, who's his former student and a total polymath. He was a consultant, then an entrepreneur, he wrote a novel, and then eventually he got his PhD and he opened his own research lab at San Francisco State University. So two just brilliant big thinkers.
Two giants. Meanwhile, while we're pumping the brakes, I think it's maybe worth asking the question, are we covering AI too much? This comes up sometimes in our conversations.
Yeah, we talk about this a lot because we only release so many episodes and there's a lot we want to cover on the show. And so we worry about this. I think we also talk a lot about, like, are we covering AI the right way, right? Are we covering it responsibly? Like, are we striking the right balance between optimism and pessimism, between hype and skepticism?
Yes. Well, I think it helps, Caleb, that I am the optimist and you are the pessimist. So there's a natural counterbalancing in there. Or maybe not always. You're right. It's more complicated than that because I have a darker view of maybe the long-term AI risks.
True. I mean, we're both avid users of AI. We're both boyishly excited about AI. I think
yeah.
I think you have, yes, more of a long-term fear of AI than I do. And I think I'm a little more skeptical about how fast AI is going to continue to improve than I think you are.
Yeah, I think that's right. And so in that sense, I think there's a really healthy tension in our views there as we approach different thinkers and different guests. But I think we both agree that we really need to keep covering this because it's mind-blowing what's happening right now.
Yeah.
And because understanding AI is so critical to navigating the world for all of us.
Yeah. And understanding humans, understanding ourselves doesn't hurt either, which is why this is a great episode today.
One indication of my enthusiasm for this subject is that Gaurav and Jay and I spoke for more than 2 hours. Because we know that you are busy and important, we've edited that down to about an hour. For fellow enthusiasts who want to hear the whole conversation, subscribe to our channel on Apple Podcasts, and you'll find the unedited version as a bonus episode in your feed, alongside the warm, fuzzy feeling that you're supporting a podcast you care about. All right, here's my conversation with Gaurav and Jay after the break.
New Vitamin Water Zero Sugar Pineapple Passion Fruit is packed with vitamins, just like the amount of peas we packed in that sentence. It's packed like your tote bag, the one you stole from your ex, or your overpriced half a studio apartment, or extra rushed rush hour traffic. Packed like your calendar, triple booked at 5, of course. Grab a Vitamin Water. Did we mention it's packed with vitamins?
Raise the rudders! Raise the sails! Raise the sails!
Captain, an unidentified ship is approaching. Over.
Roger. Wait, is that an enterprise sales solution?
Reach sales professionals, not professional sailors. With LinkedIn ads, you can target the right people by industry, job title, and more. Start converting your B2B audience today. Spend $250 on your first campaign and get a free $250 credit for the next one. Get started today at linkedin.com/campaign. Terms and conditions apply.
The family that vacations together stays together. At least, that was the plan. Except now, the dastardly desk clerk is saying he can't confirm your connecting rooms.
Wait, what?
That's right, ma'am. You have rooms 201 and 709.
No, we cannot be 5 floors away from our kids.
The doors have double locks. They'll be fine.
When you want connecting rooms confirmed before you arrive, it matters where you stay.
Welcome to Hilton. I see your connecting rooms are already confirmed.
Hilton, for the stay.
Gaurav, Suri, and Jay McClelland, welcome to the next big idea.
Thank you.
Thank you very much, Rupert.
Many of us assume that there's a little entity inside our brains, as you note early in the book, perhaps a soul or some little version of us that makes our intelligence possible. Some people have referred to this as a homunculus, a little guy in there, like a little mini-me. You don't buy it. What's wrong with this explanation?
One thing that's wrong with it is if we have an homunculus, how does the homunculus know what to do and what to think? You pretty quickly have to have another homunculus, and then how does that homunculus know what to do? And so this is an infinite regress. So just very simple logic suggests that this can't be an adequate explanation. And yet the feeling of having this controller is so strong, and that immediately presents a mystery. The feeling is there. It can't be the explanation. So what's going on?
Well, it certainly feels like we each individually reside behind our eyes. I mean, I'm tapping my forehead right now. Wow, it certainly feels like I'm right here, right? And something I learned recently that I found fascinating is that folks building robots right now have discovered through trial and error that the brain needs to be right behind the eyes in robots because vision requires so much data, so much processing. If you were to put the brain, the artificial intelligence, in, say, the torso of the robot, the lag time would be an issue given the need for the body to respond immediately to visual inputs. this is just to point out these astonishing parallels between what we're learning in parallel between what we're discovering about the human brain and how we function and what we're learning as we work to build these new intelligences.
I will also add that the nose and the ears and the mouth are all extremely close too. And I feel like we tend to overemphasize the importance of vision. Vision is like super, super powerful modality, but what makes humans so special is that they've developed ways of communicating at a more abstract level using language. And that depends on the ears and the mouth in such an important way that there probably would be really a drag to have all those systems sort of not all close to each other. And when you think of this, I look at, the two of you and I see all these organs all in proximity. And that's part of what makes it all function together as a whole.
It's just so amazing to me, that there's this saying, of course, that ontogeny recapitulates phylogeny, meaning the developmental stages of an organism, growing from a baby to an adult, looks a lot like the evolution of that organism. It seems to me we're almost seeing something analogous with technology repeating phylogeny. We're seeing the emergence of artificial intelligence. We're watching how our iPhones are becoming more sophisticated with facial recognition and robots, and we're kind of repeating the emergence of the complexity of humans in our technology in this way, right? It's kind of extraordinary. And you guys are closer to this than many people are. I mean, you've been studying the human brain and how it functions, and also artificial neural networks and how they function. Do these parallels strike you as instructive and useful?
Given my immersion in both worlds, I find that I think the more you're immersed in something, the more differences appear. And that's sort of, I'm realizing myself that for me, some of the differences are really very, very striking at this point. And this is something we talk about quite extensively at the end of the book. We talk about all the ways in which humans are still different from our today's AI systems, and all the ways in which humans understanding better how our own minds work will potentially give us a very different picture of how these AI systems are actually working in the future.
I want to say something in addition to what Jay said, because I think that the history of this, and Jay is a leading cognitive scientist and has played a very large role in the development of neural networks. And Jay and his colleague, David Rumelhart, and others developed this. They called it the PDP approach, parallel distributed processing approach, which essentially took the idea that our thoughts and actions are consequences of interactions within a neural network. They found a neural network to be very useful in helping understand our minds. Now, it turned out that approach, that framework of neural network, was adopted by artificial intelligence. Before that, in the so-called AI winter, a lot of people tried to make artificial intelligence with rule-based, almost commands. If this happens, do this. This should lead to that. And that approach didn't go anywhere because context is infinite, and one can't really stipulate what needs to happen in every variant in a given context. When AI systems were built with neural networks, which have parallels with the human and other mammalian brains, that's when, and in my opinion, that's not a coincidence, because these emergent properties come out in neural networks. That's when the AI revolution, this modern acceleration in AI systems, and for me, that's traceable directly to Jay's and David Rumelhart's and other work. And yes, Jay is absolutely right. There are profound and important differences between biological neural networks, which are also known as brains, and artificial neural networks. But I don't want us to lose the fact that they are both neural networks, and they both involve the interaction of simple processing units. So there are differences, but that base of emergence and neural networks is a similarity.
One of the most astonishing facts to me, just as a layperson reading about this and following this in the last decade, is the power of scale, and on some level, how simple the systems are. Obviously, there's infinite complexity of the brain. We're only learning it. But I think part of your thesis and part of your claim in the book, which I think is pretty widely supported, is that the mind is this emergent system, that we are fundamentally a neural comprised of, our brains are comprised of neural networks that are relatively plastic and adaptable, that it's a bottom-up process that has enabled us to do these incredible things. And in a parallel way, continuing the parallel, I think it seems like a lot of computer scientists were really surprised at the power of scaling laws, right? And the power of just expanding these networks. And you look at I think a human has 86 billion neurons. A chimpanzee has something like 28 billion neurons. We're fundamentally made of the same stuff. Would you say that at the core of the thesis of your book is that our whole intelligence is fundamentally an emergent capability based on a system that we can understand? In some sense, it's simpler than one might think. Is that fair?
Yeah, I think it's absolutely fair. And I want to tell a brief story to illustrate this point, and it's about ants. I grew up in India, and there was no social media, and there were trains of ants that you could observe and look at. One of the things that independently I discovered and then later read about is that if you put an obstacle in between a train of ants, the ants will initially divide 50-50, the long way around the obstacle and the short way around the obstacle. But in a few minutes, most of the ants are taking the short way. And to me, this was a mystery. I asked my parents about it. They didn't know. I asked other people. They speculated about some kind of communication. I didn't know for many years. We describe in the book that we can understand this behavior by pheromone trails and why the pheromone trail is going to be more concentrated and the short path. This is an example of an emergent process, right? So none of the ants has the understanding of the short way, but acting in a colony, they can, by simple interactions, lead to this emergent process. And for me, the beautiful thing was that wasn't just saying that, it's emergent. One could trace the emergence from the simple properties. So you assume some simple properties, such as ants lay pheromones and ants follow the strong pheromone trails, and you see the behavior that you want to explain emerge from those interactions. I was really attracted to this thought that maybe our brain is like that, and this was before I had met Jay. And every neuroscience class I took was not like this, right? So it was very much like this brain region does that. The hippocampus does memory, which begs the question, well, how or what's it doing? And so this metaphor of a colony of ants interacting, leading to an emergence. And emergence is ubiquitous around us, right? Galaxies are emergent consequences. Water is emergent, the properties of hydrogen and oxygen. And I think you're absolutely right. You make scale and you give these systems a lot of interactive power, and they do things that at scale that they don't do at smaller scales. And in that sense, these are emergent systems. And hence the prominence of emergence in the title of our book, The Emergent Mind.
If I could just say a few words about this scale issue. There are two very distinct views about, how to think about what makes humans special. One of them is that some mysterious event occurred that created this divide that separated us from all other species. But the other view is very much related to this scaling idea. And that view states that there's powerful and interesting scaling relationships as you look across the evolutionary history of the mammalian line, where, the systems that we share with other species have expanded, like linearly to scale up with the weight of the body. But the systems that sit on top of those, so for example, comparing our brain to a macaque monkey brain, the primary visual cortex in the macaque is a huge part of the brain. The primary visual cortex in the human is much smaller in comparison. And what's expanded is all the parts in between the things that existed in earlier species. So we're building on top of shared mechanisms an extensive network of newer processes that include language, but also include our ability to plan in long-range terms and to organize our thoughts into memories in novel ways. And it's the ensemble of new things that have evolved working together rather than one individual one that really has created the intelligence that emerged as the human species emerged.
Let's talk about how this ensemble that is the newer portions of our brain function. For me, a real unlock in reading your book was your description of how we store words with patterns of brain activity we call distributed representations. And I think just getting into this sense of how it is that the neural networks that are our brains are storing information and how we differentiate between different objects and different words. Of course, Chomsky believed that there were parts of the brain that specifically evolved for the purpose of language. I think your view is different. Do you want to describe how this process works and how our own biological neural networks process information?
So the concept of a distributed representation is one that people have historically found extremely difficult to grasp. It feels very straightforward to say, oh, I recognize my grandmother because there's a neuron in my brain for my grandmother. But the perspective and I think Jeff Hinton, really his core idea and contribution was to follow that idea that just like a piece of film can potentially store many images that can be unlocked by the right cue, the idea of a distributed representation is the idea that the connections among a network of neurons can also store many different patterns. And with the right cue, each of those distinct patterns could be brought to mind. And so in the book, we work very slowly and systematically up to bringing people into this idea about how a pattern instead of a single neuron could represent something.
I want to say that the pattern point that Jay is making is so important because it allows for similarity, right? If we had one neuron for a mango and another neuron for a peach and another neuron for a table, they'd all be distinct from each other in equal ways. They're different neurons. But if we have patterns, then one can imagine that the pattern for the fruit share commonalities that distinguish them from other categories like furniture. And indeed, artificial systems use this idea. So the equivalent of a distributed representation for a sofa and for a couch, the pattern that large language models would use have similarities. They're similar to each other. This is the importance, right? So when I learned distributed representation, I thought, oh, maybe it's a more efficient way of storage. No. It allows for this similarity. And once we can do similarities, we can do categories, right? So we can say, oh, all dogs are kind of like this. And when we have to retrieve a specific dog, well, we retrieve parts of that pattern, but also patterns that are specific to that dog we're thinking. This power of getting away from one thing for one idea unleashes a lot of what human cognition and now artificial cognition does.
It's really powerful, your description of it in the book, and this sense that let's say we're looking at different types of birds, right? That as I understand it, as I'm looking at a canary and a robin and a cardinal, that many of the same neurons would be lighting up in my brain with some subtle differences in degrees of activation. And there's both efficiency to using the same neurons, right? But there's also, as you say, this ability to register degrees of similarity and eventually build categories, and on top of the categories, really sophisticated taxonomies, right? And so our brain is moving all the way up to the broader category of birds, the broader category of animals, the broader category of things that move, right? And so we end up building in our brains this very sophisticated taxonomies of how the world works, sometimes with emotional associations and so on. And it's all bottom up. It's not top down, right? Which was not necessarily the way that all neuroscientists saw the brain functioning decades ago.
One of the things that I'd like to bring out about what we've learned from cognition that makes me think that this idea is such a good one for understanding our own mental representations is the way in which people lose information about things when they're suffering from neurodegenerative diseases. And one thing to just start with is that there's a part of the brain in the temporal lobe, the part that comes down on both sides of the brain near the tip of the temporal lobes, where it appears that we bring together inputs from all the different modalities of experience, audition, vision, sense of smell, even the sense of like the fear response I might have to something. All these different kinds of inputs converge here, and the patterns of activation on the neurons in this region kind of represent, how we think of the concept as a whole. So, my representation of a dog includes how it moves and what happens when I throw a Frisbee to it, and, what it sounds like when it barks, and how it smells when it jumps up and licks at my face, and how I feel about that, which a mixture of enjoyment and a little bit of fear, but there's millions, probably around 1 billion neurons in each side of your brain working together to represent this dog when it jumps up at you like this. And wow. What happens in these neurodegenerative diseases is that those neurons die off progressively. And over time, there are fewer and fewer of them. And as a consequence of that, people begin to lose their knowledge about these concepts, but they don't lose the knowledge about a particular concept in an all or nothing way. They lose the idiosyncratic things about it before they lose the fact that, let's say, it's a animal or even a fierce animal. So they would lose the difference between a lion and a tiger, but they would know that these are both like fierce animals, right? That one has stripes and the other has a mane, right? But they would still know to keep them separate from the cows and the deer and the sheep, who are not fierce animals and things like that. And as that disease progresses, those differentiations get weaker and weaker until they can hardly even, distinguish birds from land animals anymore in those categories. But at that point, their cognition is so profoundly impaired, and they've only got like a fraction of these neurons left.
I just want to, because the initial question you asked, and Jay took us to one side of the developmental trajectory, which is degeneration. And I think there's the other side of the coin, which you started to talk about as well, which is we start with these concrete instances. Here's a dog, that's a bird. Okay, and now we have similarities between birds, and now we get the concept of birds. And that eventually leads to formalisms, and often linguistic formalisms, about birds fly and dogs have tails. And then we start to make rules of logic, like if all men are mortal and Socrates is a man, then Socrates is mortal, that kind of things. And we tend to think that that is the calculation of the mind, right? That the mind is a logic engine that we're somehow given. And this idea of building from the bottom of concrete instances suggests that this formalism that we think of, this logic that we think of ourselves as logical creatures, that too has emerged from these concrete instances and concepts building on these concrete instances. So just as Jay is talking about neurodegenerative diseases as one when there's destruction in connections, when there are connections that continue to build up, what we get is something akin to formal reasoning. And the neural network view of the mind is saying, yeah, the formal reasoning is also an emergent consequence of simple interactions, even though sometimes it feels like it's the mind.
Right. And I guess there's a debate between some neuroscientists about whether all of logic and math and our ability to, comprehend the world is emergent in this way you're describing, or if there's a more structured capabilities that we have specifically for reasoning or mathematical skills. Is the view that you're articulating prevalent? Is it the majority view at this point, or is it a minority view?
So I would say that this debate raged most fiercely in the 1980s. And I think that the introduction of our PDP work in the middle of the 80s really triggered an outpouring of an explicit articulation of the alternative perspective. There was a man named Jerry Fodor, who was this huge, imposing man. He was trained in philosophy, and he got a hold of the first chapter of the PDP book, which was in draft form, because I was visiting MIT, where he was holding court. And the first line of the book was, "Why are people smarter than machines?" And he immediately rejected the entire thing because he thought that this machine that Alan Turing had introduced, the Turing machine, was the essence of intelligence, and it was already a solved problem. Turing's machine was this machine that could follow rules that were specified in sequences of ones and zeros on a potentially infinite tape. And this sort of was a mathematical way of reducing the complexity of thinking about thinking to something that, could be set up in a simple device. And it's been very powerful for sort of arguments about algorithmic complexity and computer science and things like that. But the idea that in principle, we understood intelligence because we understood that, what those machines could do was, I think, and remains for some, a real divide. But for me, the alternative is that what those machines do, these ideas of logic even, that go back before we had any machines that could do it, of course, Aristotle and Plato and others before them were thinking about the rules of logic. Those things are things that people constructed in thinking about their own intuitive thinking as ways of making it more precise and algorithmic. And the pushback there of the PDP idea was that those things are intrinsically brittle. They're not sufficient to allow you to build a system that is sensitive to the nuances of actual experience and that knows how to deal with the exceptions as well as the patterns of things that follow the rules. And that's what is beginning to be addressed by the AI revolution. Because once these models start having intensely, very well-structured, idiomatic conversations with people that feel like they're talking to us in natural language and in very natural and intuitive ways, it's like, yeah, they have absorbed the regularities, the nuances, the patterns that exist in language and that really can't be well captured by those rules.
What I think you're saying is that the evidence that the frontier LLMs, the most sophisticated AIs today, are now able to think with levels of logic and mathematical accuracy and so on. They're not perfect, of course, but increasingly wildly impressive in terms of their ability to take on SATs and LSATs and math Olympiads and every other metric. And the fact that this level of cognitive capability is emerging in this emergent way that's similar to what you're describing as the way that the neural network of the human brain functions, that this provides corroborating evidence that we don't need separate biological modules in the human brain to explain these capabilities.
So our brains are diverse. They have definitely parts that are primarily involved in, let's say, receiving the input from the retina, for example, or from the ear, or controlling the mouth and producing articulation. They have integrative areas that bridge between them in many different kinds of ways. We already talked about one of those, right? But what I think I'd like to emphasize is that human beings began at a certain point in history. And I find myself fascinated to trace back, when do we know that this first started to occur? Presumably they were having discourse about it, but language wasn't written down, until, the earliest sort of written records are like 5,000 or 6,000 years ago. And they're usually sort of notations about bookkeeping and things like that. Like John owns 1,075 sheep and Bill owns 23 or something like that. But the emergence of written systems that allow people to keep exact records and develop number systems and develop explicit notations and rules and so on, then make it possible to sort of derive things like mathematical proofs that something is always true. You can't do that. You can't prove that something is always true without the right set of rules and relations. In natural life, there can be a dog that doesn't have 4 legs, but having mathematical assumptions allows you to make proofs about things in ways that natural intelligence sort of doesn't. And it's our ability to internalize these systems of reasoning. That's what the networks do. They don't have them built into them as modules for reasoning. They build those things on top of the distributed representations that we were talking about through the way they are taught on problems and structured information that was generated by human beings. So language models are as good as they are because they're trained on lots of code and lots of actual math solutions and things like that. It's not in the mechanism, it's in the data. And humans invented that data. So mathematics itself is an emergent construct of the human mind.
So my early training was in mathematics. And one of the biggest questions that we are routinely confronted with is mathematics invented or discovered? And what Jay just said is look, these intuitions that we have, they lead to the rules that we apply on assumptions that come from our intuitions, observations of the world. And in that sense, mathematics is an invention. It's a cultural invention based on problems that we're trying to solve. This farmer has 5 sheep, that has 7. This is this plot of land. We need to divide it into 2. We start getting tools to solve problems we want to solve. And then we formalize those tools and we invent systems. What's lost in this, which I don't want to ignore because it's easy to ignore, is that the universe has regularities and that mathematics is allowing us to perceive and behold those regularities. So to simply say mathematics is a social construction misses the point that the universe has regularities. Mathematics is a social construction that allows us to describe and use the regularities of the universe that we live in, right? So it's a nuanced answer. The mathematical systems, assumptions, come from our intuitions, which are product of concrete experience.
Effectively, is it fair to say that our brains build models of the world, right? I mean, we take in, through sight and sound and smell and language, all this information about the world. we're building a model of the world. We end up building these categories, taxonomies, rules, comprehension. And something that I find quite fascinating is, as far as I can tell, though AI, large language models, have a lot of differences with the human brain, they too would appear to be building models of the world in a similar emergent way. There was this fascinating moment when Anthropic last December, I'm sure you saw, released a paper about, they were trying to figure out what language Claude thinks in, which as a layperson, I thought was astonishing. I was like, you really don't know. Like Claude speaks 27 languages, and they didn't know what language Claude spoke in. And when they got under the hood, what they concluded was, oh, well, what we see when we see the Golden Gate Bridge, or when we see a canary, if we can identify the clusters of units that are lighting up when those concepts emerge, we're seeing every language and its own symbolic language. So these large language models, as I understand it, are building their own sort of bottom-up models of the world that are making it possible for them to do pretty sophisticated things, like actually developing a theory of mind, being able to predict how different humans in a hypothetical scenario are likely to respond emotionally to each other. There's a lot of sophistication that has emerged out of this process of observing, building taxonomies and models of the world in ways that are kind of shockingly analogous to what we seem to be doing. Am I wrong?
Absolutely. I think you're right. One of the things that is so striking is that you're surprised at, wait, don't you know what language that's thinking in? This intuition comes back from our reflections on our own minds. We have access to the conscious mind. And we're attracted like moths to flame to this idea that the conscious mind, often the linguistic image-related mind, is the mind, right? And what the emergent mind, the case we're making is that, look, there's a lot of interactions and activations, and these activations produce thoughts and ideas, some of which also make it to the conscious level, right? So it's an illusion, perhaps, to say that what's in our conscious mind is reflecting the operations of the mind. We're saying that the activations that are in there, the models that you're talking about, produce these thoughts, and some thoughts do rise to the level of consciousness.
As a sports fan, I have to confess, sometimes the game gets kind of boring. That's when I unfold my Samsung Galaxy Z Fold 7 and use multi-window viewing on its large screen. Boring game? I'm checking out my fantasy baseball league at the same time. Score still 1-0. I'm replying to emails in the other window, scoring points with the boss. Semifinals finally getting exciting. I'm buying tickets to the finals and booking my flights. Can your phone do that?
The new Galaxy Z Fold 7. Get yours at Samsung.com.
If you thought goldenly breaded McDonald's chicken couldn't get more golden, think Golder, because new sweet and smoky special edition gold sauce is here. Made for your chicken favorites. At participating McDonald's for a limited time.
Something else that just astonished me in the book is that you're in this explanation of our brain and how it works. Everything that is us is physically manifested in the brain. So if you were to look at, say, what's triggered when I think about Coca-Cola, right? When I think about Coca-Cola, which you write about in the book, is an interesting case study, I probably have a set of neurons that lights up. It's a little different for each of us. I may have an association with drinking Coca-Cola the first time I kissed a girl in, 1982 or something. But people tend to have an association with it's sweet, it's cold, it's cola flavored. But we also might associate it with fun and friendship and the color red. And it turns out that the Coca-Cola company spent billions upon billions of dollars in order to build those associations in our brains. And because these connections are bidirectional, the color red might just cause me to think of Coca-Cola. But I find it fascinating that there is a physical representation effectively in each of our brains of the entirety of who we are and how we perceive the world. Is that
That's
accurate?
exactly right. And the idea that, thinking about a Coke can make you think about this intimate time you had with a friend. That's what they spent all that money on, right? I want to teach the world to sing in perfect harmony. I'd like to buy the world a Coke, could keep it company. It's the real thing.
I like to teach the world to sing in perfect harmony. And I'd like to buy the world a Coke and keep it company.
Yeah, what this brings, Rufus, is it's physical, and again, this gets back to we're a part of the universe, and we want to understand ourselves in mechanistic terms, right? So we want to understand our decisions in mechanistic terms, and this episode you're talking about with Coke sort of brings to light the question of how we decide things, right? Which is, do we decide things based on a calculation of value, or is our decision an emergent consequence of the song Jay just sung and, the girl you kissed in 1982 and the sweetness that we feel in our current bodily state? And what we argue in the book is that a great way to begin to understand why we do the things we do is to use this emergent machinery of the neural network, in which all of these associations, some value-related, some habit-related, some related to the internal state of the body, some related to what we just saw a second ago, conspire together from which a decision emerges. And this is a different way of thinking about why we do the things that we do. I mean, the economic idea is we do what brings us value, right? What we're suggesting is that a lot of these connections and activations may be what we would call value-related, and then many of them are not. And our actions are an emergent consequences of this interaction.
The strength of connections between neurons are those represented physically. We know that there are some people who are spending a fair amount of money to freeze their brains, right? and in the cryonic community, they say these individuals are not dead; they're de-animated. Do you think it's possible that in many decades or centuries to come that we could reanimate frozen brains?
I don't see there being an intrinsic reason why it's impossible, but we're far away from it. People have tried to sort of use pig brains. We talk about this in the book a little bit, where they've sort of been able to reanimate 6 neurons.
Yes.
And that's far from reanimating an entire brain.
Let's talk about some of the strengths and weaknesses of the structure of our brains we've been describing and how our memories work. On the one hand, it's just amazing that our brains can do all that they can do, that we can remember as much as we do. And as I learned reading your book, in the memory network, we can do something called similarity-based inference. And the way that these units of memory function, and I'm going to say this badly, but you can correct me. I have an association with a friend. I have their name, a set of experiences or associations I have with them. Their profession, a whole network of memories. And I found that if I'm trying to remember someone's name, the more things I think about them, the more likely it is that the name will pop back in my head, right? I mean, it's a network of bidirectional connections.
Absolutely.
And there are advantages and disadvantages to the system, right? There's sometimes sort of biases and lapses of memory and things that we experience. Can you speak to that a little bit?
You've touched on something that's really, really, I think, very, very central to the way memory works. It's something that makes memory in the human brain very, very different from the conventional way we have of thinking about memories, where one way of thinking about it is they're like documents that are stored on a disk drive or something like that. Each location has a physical address, and then what you stick in it is completely arbitrary with respect to that address. With distributed representations in the brain, at least the way I think about it, it's all content. So you can access it from different aspects of that content. Now, some of that content is the context in which the experience occurred. So you say, oh, well, that's the address. And that's the way some people have tried to argue about it. But if it's like, oh, that's a particular smell or the aroma that I experienced, that can trigger that whole experience too. So you can access it from any element of that experience. So then why do we have so much trouble accessing the particular experience we want at any given time? Well, one way to think about it is that for many things like the taste of coffee, for me, which I have so many times every day, it's associated with so many different experiences that would never trigger the one that I'm looking for out of billions and billions of experiences just drinking some generic cup of coffee. But if I come up with some other cues to a particular experience when I was drinking coffee, then they can start to work together to rule out all these other things that are sort of blocking our access. And then once you have a few cues, they can conspire together to bring that thing back to mind.
2/3 of Americans think that memory is like a video recording, right?
Right.
People have measured it, and people have asked for metaphors, and about 2/3 of people think it's like a movie. It's less like a movie than really old bullet point notes that you get access to. And from those notes, you construct the episode, right? So memory is a construction. We make mistakes. We misidentify people in police lines. It's a construction. But it is this malleability, this flexibility, this constructibility of memory that is also its strength, because it allows us to make concepts, to say, I've seen 18 things like this, so the 19th must be like this. This is the remarkable capacity that our system of memory gives us that a computer-like memory is not going to have, where every record is separate and therefore not leading to this generalizable capacity that we have.
Although artificial neural networks would potentially behave this way, which explains why they hallucinate. My wife has found it amusing to note that I'm just horrible at coming up with the names of all the parents in our children's school. But she said, "But honey, you have a remarkable ability to remember everything you read in books."
Yes, you do.
And one of the things that has struck me, because I find my own memory, as I think so many of us do, simultaneously kind of impressive and embarrassing. and,
absolutely, mine is
and
terrible.
Frustrating, right? but one of the things that struck me reading your book is that it would make sense that as we build expertise in a given field, the more knowledge we build. I mean, my wife has sort of like perfect knowledge of all the parents of, in our kids' school. And she's also fantastic at remembering producers and directors and cinematographers and actors in films, which I can never retain. But when she hears about a new film, she has wildly more points to connect that new piece of information with, right?
There's a lovely experiment about this where they showed chessboard configurations to chess experts and novices. And the memory task was, what was the position of the various pieces? And it turned out the result is beautiful. The result is that if the pieces are placed randomly, there is no difference between expert chess players and novices. But if the pieces are placed as they might occur in a naturally progressing game, then the experts are vastly better memorizing than the novice. And that's exactly right. I mean, there's hooks that we have. One state is linked with the next state. There's these auto associations, and memory is domain specific. My memory for spatial navigation, however, no matter what I do, is terrible.
Let's talk about how different human brains and large language models are. One difference you point out is that the training data for the typical large language model is 100,000 times larger than the training data, than the information that we process as a human brain, which on the one hand is sort of impressive for the AI. On the other hand, we're clearly dramatically more efficient at learning. How do you think about the sort of the strengths and weaknesses of AIs today by comparison to the human brain?
Humans have goals. We generate goals. And a lot of our actions and thoughts and behaviors are in service of those goals. Now, it's very interesting to think about where do these goals come from. They're not in some homunculus. They themselves arise as abstractions from our experiences. But once they arise, they play a deep role in shaping what we do, what we think, even how we perceive. That same mechanism does not guide today's AI system, right? I mean, to a large extent, their goals are the goals you give it. And this is dangerous territory, right? We want to be very careful about AI systems that have their own goals. But right now we're talking about what are the differences in our cognition and a large language model's cognition. And for me, this is a central difference.
I wanted to just say a little bit about the way the large language models learn, which I think is very, very different from the way our brains learn. To try to paint this picture, I want to start by trying to get us to envision the system in a large language model. It's got this huge stack of neural networks. So, for example, GPT-3, which was a predecessor of the model that was released in 2022 that sort of really broke open the ChatGPT sort of environment, had 96 of these modules. And each of these modules had a complex neural network embedded within it with hundreds of thousands, even millions of connection weights that are the things that allow the model to take a sequence of inputs and make predictions about what the next input could be. The way they train these models is they give them very, very long sequences of text. And the model at each word position, it's using all of that previous context to predict the next word. When it makes an incorrect prediction, there's a signal there. Oh, I should have said cream instead of milk or something. And that sends a signal that goes to every single connection weight in the entire network, as it was aligned with every single token in the context. And some tiny, tiny adjustment is proposed for each of those connection weights. Now, some of them get zeros or something infinitesimally small so that nothing happens, but others of them get, slightly larger signals. And that's the information that the network uses over each time it's exposed to the predicting the very next word. It's generating these massive ensembles of these signals. Something like that could be happening in our brain. I think it's very likely to be true that something very much like it is happening, but it's a starting place for a conversation about what those differences are.
One question that emerges for me is, what is to stop these systems from becoming super intelligent? I mean, people love to say, point out how dumb and wrong these systems can be. But at the same time, they're just astonishingly impressive, and they're just babies, right? We're building these new systems that are just countless orders of magnitudes faster, ingesting dramatically more information. Yes, less sophisticated in some respects, but do they have the potential in your minds to become vastly more intelligent and capable than humans?
One thing we have are bodies, right? So these artificial systems don't have bodies the way we do. And when we think about much of our behavior, it comes from our needs, right? So needs are very powerful engines of goals. So if need detectors are saying, wow, there's a lot of salt in the blood right now, that is a stand-in for thirst, that set of neurons starts signaling, which then with other neurons that are detecting opportunity for liquid water-like things, give rise to action. There's a tremendous role of the body in terms of not just the needs, but the neuromodulators and so on in instantiating goals, which I referred to earlier, because I'm coming back to goals in this context because I think goals are so central to our intelligence. And is there a fundamental reason why a artificial system can't have goals? No, there isn't. I mean, you could probably have stand-ins for neurochemicals and so on. My view on this is that it's helpful to treat these as tools, to manage them as tools, to understand that when we give it autonomy, it should be in prescribed and thoughtful ways. If we are a process of the universe, then we can recreate those processes in artificial system. If you subscribe to the idea that there is no magic stuff, then there's nothing stopping an artificial system from being equally or more intelligent. One thing that we have that the current AI systems don't have, which is very underappreciated in terms of our own intelligence, is our body, because it leads to our motivation and it leads to our goals. And while AI systems are meeting and exceeding us in cognitive domains, this is not the case in motivational domains.
Running a business comes with a lot of what-ifs, but luckily there's a simple answer to them: Shopify. It's the commerce platform behind millions of businesses, including Thrive Cosmetics and Momofuku, and it'll help you with everything you need. From website design and marketing to boosting sales and expanding operations, Shopify can get the job done and make your dream a reality. Turn those what-ifs into... Sign up for your $1 per month trial at shopify.com/special offer.
This episode is sponsored by Friskies, who would like to tell your cats hi. Now, if that didn't get your cat's attention, there is one thing that always does the trick. Just pour some Friskies crunchy food in the bowl and you'll hear those paws come running. Works every time. With so many Friskies choices, you can always bring your cats running from their secret napping spots. There's always more to explore. See for yourself at friskies.com or visit your local store.
Let's talk about consciousness. You assert that consciousness does not appear to be necessary for humans, that our thoughts and actions appear to precede our conscious awareness of them. Am I getting that right?
I am deliberately agnostic about this. So this is one point of view. There's two ways to see the question. One is to say, well, when we build our machines and we get them to do tasks and things that we want them to achieve, the appeal to consciousness per se is not, it's not on the table. It's not what people are doing. They're looking for better ways to assess whether the network was successful at solving the problem or something like that, right? And cognitive science has proceeded in that way without needing to reference consciousness. Yes, many people talk about it. There are scientific communities of scholars who want to get together and talk about consciousness. So on the one hand, you can make a lot of progress without it. On the other hand, why would it exist if it didn't have a role? So that's the dilemma that I always find myself in, and that's why I express agnosticism about this. I see these as equally powerful arguments.
If you read the book, we make the case about how our memories, our ability to detect context, our ability to make concepts, our ability to make decisions, rely on activation. And activation by itself is not making any suppositions about being conscious. Activation is an idea that's inspired by the action potentials of neurons. And it's very difficult to see how the action potential of neurons results in the subjective experience that we have. What's remarkable about the story we tell in this book, I think, is how far we can get without having to rely on this subjective experience. Now, people who study consciousness distinguish two kinds of consciousness. One is awareness aspect, right? So I'm aware I'm talking to you. I'm aware of listening to what you both are saying. So there's an awareness concept. And then there's this subjective experience, phenomenological concept, which has to do with the greenness of green and the redness of red and the smell of a rose and so on. And I think it's really useful to sort of think about functionally, what role are these playing? Because it's a large leap to go from activation in units to conscious experience. And I think it's very useful to think about what is the functional role that consciousness plays for us. So, for example, it may play a role in enabling communications between different processing subnetworks in our brain. So let's go deeper into the functional aspects, because the how question for consciousness is the famous hard problem. But I just want your listeners and our readers to take away this idea that it's very possible that the same activations that are giving our thoughts and actions are somehow creating this conscious awareness and experience. And indeed, there are experiments in which conscious experience tends to be correlated with lasting and stable states of activation. So activation seems to be related, some patterns of activation seem to be related with conscious experience. But how exactly they are is not yet known.
That's right. And as you say in the book, there are studies showing that people make decisions before they're consciously aware of having made decisions, right? So and you ask the question, what utility would consciousness have? And among the possible answers are pleasure and pain could be useful. Now, of course, large language models have instructions and goals, rewards or succeed or fail at a task. But an argument could be made that excruciating agony or orgasmic pleasure might be great, larger, more effective rewards and more motivating. But right, so that would be one explanation. Another one that I find kind of fascinating that you bring up is this notion that having a more global comprehension of ourselves, we develop a theory of mind to understand other humans, predict their likely future behavior. That theory of mind we can reflect back to ourselves and have a comprehension that we ourselves are individuals that display consistency of behavior and consistency of goals over decades, right? And that perhaps there's utility there.
I like everything that you're saying, and I just the idea that, because it hurts, that motivates me to avoid it. It gets us back to that homunculus problem.
Right.
And that's where I find myself really wanting to sort of like stay away from there.
That's right.
It's like, okay, I don't want to have to imagine that there's a little me who's deciding that hurts, I better stop stepping on that nail, right? I know that actually I have reflexes in my foot, which will, a very sharp prick into my foot will get my foot to start coming off that nail before the signal even reaches my cortex, right? The spinal column has taken care of that for me. So I know that I have systems that in really primitive settings like that, at short time scale settings, are helpful in getting me to behave in appropriate ways without me needing to invoke my conscious mind as a part of the whole story. And so this is where I'm like, okay, well, let's deconstruct this. Let's try to get deeper into what it is that about that. Yes, we have the experiences. We're not denying that in the book, right? I myself have an extremely rich experiential life of the kinds of things that you've referred to. And yet the role that they play causally in my behavior is something that's where I feel like agnostic,
Well, and this, of course, leads to another obvious question, which is, could artificial neural networks develop consciousness? Number one, and number two, does it matter? As we're thinking about superintelligence and the evolution of artificial intelligence, is this just a red herring? I mean, it's interesting, obviously. We all love to think about it.
Yeah.
So I pose these two questions to you. Do you think that AIs could become conscious, and does it matter?
So the pleasure and pain thing that you and Jay were just talking about, I think it's a really good test case, right? So I just want to underline, because I think Jay's point is very, very relevant, which is who's experiencing this pleasure and pain? What like if we want to give it a causal story, who's experiencing? And that's a trap, right? That's a trap to the mechanistic way of thinking. And yet you can't deny pleasure and pain. Now, I was reading a paper just a couple of days ago, and the case they're making is that neuromodulators in the brain are released when a need is satiated. And I'm talking about hunger and thirst, not because they span motivation, but they're simple to understand and reflect on. So when we find thirst detectors come back, there are neuromodulators getting released, and they enhance learning and activation and so on. A lot of motivational behavior occurs because of these neuromodulators. And the paper makes the case that for need detectors to come back to homeostasis is a long time cycle. You want the organism to be responding faster. So pleasure and pain are hacks in the sense they're heuristics to signal to the organism, this is good and this is bad, right? And what exactly those hacks are, TBD. But my point is that because we can get so far in understanding cognition and action without resorting to pleasure and pain, says that maybe it's not as important as we might have naively thought, because we have access to our conscious brain and we think without consciousness, how do you even get started? And indeed, I think a lot of the rule-based reliance of earlier AI is about conscious systems. So it may not be that important. I think the question gets solved by going deeper into the exact functions that conscious experience plays, including pleasure and pain. There are philosophers such as Daniel Dennett who talked about it being an illusion, right? So Dennett says famously about a root canal, something like, take away the fact that it interferes with my attention. Take away the fact that it keeps intruding on my thoughts. Strip away all of these properties from the sensation of pain. Are you still left with the subjective experience of pain? And he argues not. I'm agnostic on this, but I think I am a functionalist on this.
You quote in the book the Google researcher and his conversations with the precursor to Gemini, the Google AI, that he was convinced was itself conscious. Might there be any little inklings, any little sparks of consciousness, as people have said, in current systems?
I want to give the answer you offered me the chance to give before, which is I don't think it makes a lot of difference.
Okay.
I think that what matters is that when the models engage in patterns of behavior that we find trigger things that we have conscious experience with respect to, and we experience in our interactions with each other, like when Rav tells me something about his feelings about loneliness or something, the way the computer told Lemoyne, we attribute this self, this special thing, this homunculus like creature to the other in ways that, ultimately may not be more helpful than taking a functionalist perspective, as Rav has argued, and asking ourselves, okay, it's the attribution is coming from me. It's not in that machine. It's coming from me.
Yeah. I'm interested to know how concerned you two are or are not about AI safety as we continue to increase the capabilities, improve upon these AIs. You at the end of the book, you do refer to the importance of developing AI responsibly, but I don't hear the level of alarm that I've heard from some other guests we've had on the show. What's your view about sort of the current trajectory and how concerned we should be about interpretability, transparency? Like, you all are working hard to make the human brain transparent to us, to be able to take the lid off and understand what's happening. We're building new kind of intelligent organisms without fully understanding how they function. How alarmed should we be about that?
AI is a tool. If you put the tool in the hands of bad actors, bad things are going to happen. And so we should worry about people. when people worry about AI, they often paint scenarios of AI having goals of its own and it ignoring or going against human goals, right? That's where the anxiety really comes to the fore. We ought to also equally, if not more, worry about AI being, this deep fake videos, destroying the social fabric with information overload and so on. So there's all of these bad things that can happen. As far as it comes to AI autonomously acting, I feel like there is a point of view that I want to put forward that maybe we're in a bottleneck moment. We think that this exponential rise that we've seen in large language models is going to continue ad infinitum. But a lot of the data that was used to train these has already been used. What we don't have is data on actually doing things in the world. When we have a drink of water, we're not labeling why we had that drink of water. So there isn't that array of labeled acting in the world data. Now, is there anything deep about AI never being able to do that? No. But I also think AI lacks, current instantiations of AI lacks goals. Current instantiation of AI has used data around it. And so there is a case to be made that let's worry a lot about the policy, how we use AI, how people use AI, and not so much, in my opinion, about the doomsday of AI acting autonomously somehow to wipe out humanity.
Let's talk about how what we've learned about the human brain can help us live happier and more effective lives. This section towards the end of your book really surprised and delighted me. I didn't see this coming. Gaurav, you've said that your evolving understanding of the human brain has helped you reframe the way you see the world and maybe your own behavior. Can you say more about that?
I am struck by the unity of our processes, right? So if we view humans as a process and we take the neural network view of the mind, then our processes are fundamentally of a very similar nature because of our shared biological heritage. And yeah, Rufus, you and Jay have had different experiences. You have different connections that are innate. But at a fundamental level for me, what the neural network view of the mind is telling me is that we are deeply one. And this sounds a little mystical. It's not meant to be. I'm making a statement about a process, right? Like deeply, a wave is like another wave. For me, this is an invitation of default kindness. I don't need to agree with everything you're doing or saying, but if I remind myself that what you're doing and saying are emergent consequences of your input and your experiences and your biological innate connections, then my force is just only against your argument. It's not against you, because I see you as a process. So for me, what this says is, I'm going to come to any interaction with any human being. This is aspirational, with a stance of kindness and patience, because they're processes just like I'm a process. For me, the closer I can get to this aspiration of kindness and patience, the better my days seem to be, right? Like I get up in the morning and some days I get to go on a walk with Jay and have lunch with a friend. And if our days are glowing in this sense of kindness to other people, I think they glow a bit brighter.
I would like to emphasize the humility side of this. Part of the story that we tell in that part of the book is a story about somebody observing somebody else making a decision and taking an action and making an attribution to them about why they did it, and pointing out that the neural network approach allows us to see how multiple different factors could all be conspiring together to make it so that that person did what they did in that moment. But I also feel like our own beliefs that we feel are entrenched things that we hold dear and almost self-evident can themselves be the products of things that we're not so aware how they came to be. We're not so clear that their ground truth really, they could be the constructs resulting from a lot of conspiring experiences that it just makes me feel like whenever we're judging anybody, including other people, or we're thinking about explanations for anything, we have to be humble and cautious. And if we can temper our sense of certainty about things, that may contribute to our ability to live together with each other.
I'd like to close by reading a quote actually from the beginning of the book. You talk about how our brains are an emergent property of billions of cells we call neurons, animated by patterns of electrical and chemical activity that rise, fall, and rise again. You say our thoughts are patterns of activations forming, expanding, folding into one another, then perhaps diminishing for a spell, but reemerging again with the slightest new input, which you also describe as like the murmurations of swallows. And if anyone has seen those beautiful videos of thousands of swallows rising and falling, contracting and expanding like some kind of symphony, this is how the two of you see the way that thoughts actually physically manifest in the human brain. I can't imagine more magic than that in any description of how it is that humans come to be. So thank you both for your time today. Such a beautiful book and conversation.
Thank you.
You can cut this out of the thing, but I do want to acknowledge that I'm so struck, Rufus, by your questions about how deeply you've read the book. I was not expecting this. You've read every chapter, and this is like, I hope we get millions of readers, but we got one really deep one, and I'm delighted about that. Thank you so much for your reading and for this great conversation.
That was Gaurav Suri and Jay McClelland. Their new book, The Emergent Mind, comes out on October 21st.
In the episode notes, you'll find ways to get in touch with us. We love hearing from you. You can message Rufus on LinkedIn. You can send an email to podcast@nextbigideaclub.com. And we're so grateful for your thoughts, your comments, your guest ideas. So please keep them coming.
Today's show was produced by Caleb Bissinger.
Sound design by Mike Toda.
I'm Rufus Griscom.
And I'm Caleb Bissinger.
See you next week.